Okay, so now we're going to take a look at the some ideas behind inverse functions. So the first question we want to ask ourselves is, do all functions have an inverse under composition? And so when we're thinking about inverses of compositions, what that means is if I put in something into F, then I take that number, I put it into F, then when I put it through G, I then kind of invert this process, and then what I get left at the end is the original number. So what that means, and I guess in this case I wrote this as F composed with G of X, so that means that I put something into G first, then it goes into F. Do I get the same number back out to begin with? So this is not going to be as easy of a question as we maybe have seen in the past. So if you've seen this in college algebra, pre-calculus, high school, whatever you saw this becomes a little more complicated when we start to work with more abstract functions. So our definitions that we want to take a look at now is if we have F is going to map things from A to B, G is going to map things from B to A. Notice what we have going on here is that the domain of F is the same as the codomain of G, and the codomain of F is the same as the domain of G. So what this allows us to do is if I take an element from A, I put it into F, it goes into B, then it can go into the function G because G will map that back into the original set. Vice versa, if we go in the opposite direction, I take something from B, I can put that into G, that element's going to get mapped to A, then if it goes through the function F, that's going to take that element over here from A into B, and we can see does it equal the same thing as the original. So there is a reason that these two get mapped to opposite. So the first definition that we have here is that the function G is a right inverse. Okay, so already we're in very different territory. We've never defined a right inverse before. So we have defined a right inverse for F if F composed with G of X is equal to X for all elements in B. So everything that we plug into G first, we have ourselves a right inverse if we plug it into this right inverse first, then it goes through our function and we get back the original. Notice it's the right inverse because G is on the right of F. So that leads us to our next definition. The function G is a left inverse. So we have ourselves a left inverse if now G is on the left of the composition expression here, and we get back the original X here. And this is for all elements in A, which was the domain of F. And that makes sense because we're plugging them into F first. Now, what you all have seen in the past is this. The function G is the inverse. So it is the inverse for F if it is both a right inverse and a left inverse. And so we're talking about functions in this case. So indeed we have a function G that now we can start talking about what is the inverse function. So notation, F inverse, this just F to the negative 1, this is the inverse function. Now this is different. This is different because we're saying that this is now a function. This is a function. But if I put F inverse of a set Q, this was my inverse image. This is just nothing more than a set. Remember, this is not assuming that we have an inverse function. So this by itself, this is just the name of a function. It is not looking at a set that we're looking at. So be careful when it comes to inverse images and now inverse functions. All right, so we'll take a look at some examples to be able to get a little bit better of a feel on this.